So derivatives of exponential and log functions. When we first talked about exponential functions and log functions, I made a case, though not a formal proof, of the fact that if you have y equals e to the x, the derivative of e to the x is e to the x. All right, that's one of the nice parts about e to the x, one of those kind of this base e that comes up so frequently in nature, comes up a number of ways, and you can define e in many ways, and if you define it in one way, all the other ones you can prove. And so what we did was we looked at, remember we had the exponential curve of 2 to the x and 3 to the x, that they had the slopes at f equals 0 was pretty close to 1, but not really 1, and found that this intermediate number, this 2.7 number, gives you a slope of 1, and so that corresponds to e to the 0 equals 1, and so if we take the derivative of that, we have the slope equals 1 as well. Doesn't matter if you remember how to derive it. As you study calculus, you'll see e come up even more than you see pi come up. Okay, so while pi is perhaps a more famous, popularly famous irrational number, the one that really comes up a lot is e. Okay, so let's look at y equals a to the x. So I want to figure out what's the derivative of this. And so what I'm going to do is I'm going to express a as e to the log of a, natural log of a. And I'm going to make just a bold-faced substitution here. And so I'm going to have y equals e to the x ln x. Because remember, when we take a number to a ln a is from this a to the x. So I'm looking at this function. I want to ultimately get to the derivative of that. And so if a equals e to the ln a, if you do a to the x, this is going to be e to the ln a to the x, and then that simplifies to that second line that I have. Remember, it's the power to power rule where you take the products of the exponents, and so this is going to be x ln a. Okay, so if I differentiate this, I can use that definition that I have of dy dx equals e to the x by saying, okay, the derivative of e to the x ln a is going to be e to the x ln a, and then by the chain rule, the derivative of x ln a is just ln a. Now here's where the sleight of hand comes in. Remember this as being y, right? This e to the x ln a is just y, which also is a to the x. We can substitute that back in. And so here's our derivative of a general power function or exponential function where we have the derivative of y equals a to the x is just a to the x ln a. Now look at it backwards. If we said a was e, ln of e is 1, and so we get back to the same place that we started. So it's consistent with what we've started with, but that's the derivative, and that's the one that you have to remember. So if we had 2 to the x, the derivative of that is going to be 2 to the x ln 2. Okay? All right, so here's the two derivatives that you should remember, and I'd like you to do these. And these are primarily relying on using the chain rule. Okay, so these, just by applying the chain rule and knowing these two derivatives, you should be able to do these fairly straight away. Okay, so how about the second one? Almost. Well, not even almost. Okay, yes?
Like 1/2 negative 1/2 times e x, or e to the x 1/2.
Yes, exactly. So the process here is take the derivative by chain rule. Okay, so we have our e to the square root of x, and then by chain rule take the derivative of the square root of x, which is 1/2 x to the minus 1/2. And so if we want to rewrite that, we can say e to the square root of x over 2 square root of x. I know this takes a little getting used to. When you take the derivative, you just have the function first, and then you do by chain rule what that exponential expression is. How about the next one? So here you have to use the product rule. What do you think?
E to the negative x minus x e to the negative x.
I think that's, if I hear you right, I think it's pretty close anyway. So, by the product rule, okay, so first we take the derivative of x, which is 1, and then times e to the minus x. And then we retain the x and take the derivative of e to the minus x, which is going to be e to the minus x times negative 1. And so I'm just going to make that negative 1 coefficient out front, and I get e to the minus x to the e to the minus x. If I said that right. I wrote it right. Okay? Now think about this next one, how you do that. Of course, you're going to apply this particular derivative in this context. Anybody get it? Okay, so the first thing then is we're going to retain that first function, right? Just like we have a to the x equals a to the x ln a. So now we have to take the log of a, which is 2. And then by the chain rule, we're going to take the derivative of sine pi x. And so that's going to be pi cosine pi x, right? Because the derivative of sine of pi x is sine pi x, and then by the chain rule, you have to multiply it by the derivative of pi x, which is just pi. And so here's your solution. Now I'm not simplifying this or changing the order or whatever. I mean, there's nothing, I don't think there's any really pretty way to present that. You know, like usually you do coefficients and then variable expressions and things like this. So I suppose you could make this pi log 2 cosine of pi x times 2 to the e, or 2 to the sine pi x. Doesn't really matter. There's probably not a good convention to do it this way. Now you will see exponentials and trigonometric functions mixed together, and there's a very specific reason or a very specific instance where that comes up when you're dealing with complex numbers. Not that we're going to do complex numbers in this particular course, but there's a way to represent a complex number with both an exponential e to the something times some trigonometric functions. Yes, Sarah?
How exactly did sine pi of x, like, I don't understand how pi came in front of cosine pi.
Okay, so if we take the, if we just have sine pi of x, So the derivative of sine is cosine, pi x, and then the derivative of pi x is going to be just pi, right? And so I put the pi in front of the cosine. Okay, so now let's look at logarithms. And I'll derive the derivative of a logarithm. And again, I don't expect you to be able to do this, but I would like you to see where it comes from and then also remember the results. So let's do this as, rewriting this as a to the y equals x, right? That's the equivalent expression as y equals the log base a of x. So a to the y equals x. Now let's do some implicit differentiation here, because we already know how to take the derivative of this. And so if we use implicit differentiation, we're going to get this as a to the y ln a, that's the derivative of a to the y, and then by chain rule we have to do the derivative of y, and so we get y prime. Derivative of x is 1, and so we have this expression here. Now the next thing we're going to do is we're going to notice that a to the y equals x. So I can just put in, substitute that a to the y back as x, and now I'm going to solve for y prime. And I forgot to put my little prime there, so I'll add that right now. Okay, so there's your derivative of y equals the log base a of x. The derivative is going to be y prime equals 1 over x log of a. So let's say now we want to do the natural log of x. Okay, so we have y equals the natural log of x. That's going to be 1 over x times the natural log of e, which is going to simply be 1. And so this is probably the most important derivative outside of e to the x. The derivative of e to the x is e to the x. The derivative of ln x, the natural log of x, is just 1 over x. All right, so we get rid of transcendental functions completely when we take the derivative of this. All right, so let's go through some examples. Let's say we have the derivative of the log of x squared plus 1. What's that derivative? Well, the derivative of the log of a function is 1 over that function. And then by chain rule, we have the derivative of x squared plus 1 is just 2x. And so I'll rewrite that to be 2x over x squared plus 1. Okay? Everybody follow that? Now this is going to be a pattern. We're going to take whatever's inside the argument for the log and start off with just the reciprocal of that. And then by chain rule, we're going to take the derivative of this thing and multiply it by the reciprocal of that function. Okay, so now let's do the log of the sine of x. So that's going to be 1 over the sine of x times the derivative of the sine of x, which is cosine of x. And so we have cosine of x over sine of x, and here we get the cotangent of x. Okay? Next one. Now we have an outer function, which is the square root. So if we have the outer function square root log of x, we're going to first take the derivative of that outer function, and then multiply it by the derivative of the inner function, which is ln x. And so we have this. Now if I rewrite this, this is going to be the square root of ln x in the denominator, so I can write it simply as that. Okay, so now this one we can do in one of two ways, and this little kind of consequence of how we can do this in two ways is going to loom really large now. Okay, so if we just went about the way that we did the very first one, where we're going to take the derivative of the log of x squared, means that's 1 over x squared times the derivative of x squared, and so that simplifies out to, excuse me, 2 over x. Now the second way we can do this is that we can rewrite that derivative before we actually take the derivative. We can rewrite that function taking the exponent out as a coefficient. Okay, and remember, when we have a coefficient, that just rides along with our derivative. So when we take the derivative of this, it's just going to be simply 2 over x. And so we get there very directly by taking out the exponents. Okay, everybody follow here? Okay, so you should try a few now. I want you to find the derivative of these. I'll give you a few minutes while I'm... Okay, so the first one takes the product rule. So the product rule of this is going to be take the derivative of x, so we get ln of x, and then we take x times the derivative of ln of x, which is we get x over x, and the derivative of minus x is 1, and so the 1 minus 1 gives us just ln of x.
Okay.
So the next one, would you take the reciprocal of 1 over ln x, or would it be 1 over sine?
It's, oh, for the next one? Okay, so the first thing we're going to do, it's a chain rule problem, right? So the first thing we're going to do is take the derivative of sine, which is cosine of x, and then you multiply that by the derivative of the log of x, which is just 1 over x. Okay, so we just get cosine of log of x over x. Okay, how about the next one? If you remember what the formula is, the derivative of the log base 2 is going to be the reciprocal of the function times log of 2, right? So that's the first part. Then we have the derivative of 1 minus 3x, which is negative 3. So we'll have that. Okay, how about the last one? Now the last one, you can do it two ways again. You can take first the derivative of the log, and then the derivative of the square root, then the derivative of x plus, or x squared plus 1. You know, we're using the chain rule twice. Or, better, recognize that the square root is to the 1/2 power. Okay, and then we can take that out as a coefficient. So first rewrite your expression like this, then it becomes way easier. All right, so now we'll take the derivative of this, and we get the 2 comes from the 1/2. Then the derivative of the log of x squared plus 1 is 1 over x squared plus 1 times the derivative of x squared plus 1. And so then the 2's cancel, and we have an x in the numerator, and we just have x over x squared plus 1. All right, everybody have that? All right, so let's go. Now, let's look at this. Think in terms of how can we simplify this thing before we start. Now, this chart is going to be a chart from hell, and it's to show you what happens if you just do it the way it's written, okay? So you don't even have to take notes on this particular chart, but just follow along. What I'm going to do is I'm going to take the log of this expression, and then I'm going to use the chain rule, I'm going to take the derivative of x squared over the square root of x plus 1. And you can already see by using the quotient rule on that thing is going to be kind of a mess, right? So take the derivative, that's by the chain rule and by the quotient rule. Okay, so this is the derivative of the log part of that function, and then take the derivative of that inner function, and we get this by the quotient rule. And so the rest is simplification. And so I get this. And then factor out an x and cancel that out, and I get 3x plus 4 over 2x plus 1. Okay, I defy you to do that in one pass without making at least a little mistake, right? I mean, that's something that, you know, I took my time on this one, and I had a couple misstarts on it, you know, and finally I got what I intended. Now, this is not an unusual kind of expression. You'll see this kind of thing a bit. But there's a much, much easier way to do this. In fact, it becomes so easy that I hope you never, ever do what I've just shown you here. Okay, so this is the way that you should do this. Okay, so the first thing we want to do is we want to expand this by using our rules of logarithms. Okay, so this is going to be y equals 2 log of x minus 1/2 log of x plus 1. Okay, everybody see that? Okay, this is why we did all that stuff of expanding them into terms. Now, if I take the derivative of this goes really fast. And I'm done. Derivative of 2 log of x is just going to be 2 over x. Derivative of 1/2 log of x plus 1 is going to be 1/2 times x plus 1 times the derivative of x plus 1 is just 1. So I'm there, okay? Now, so we're done here. This is a perfectly good answer. But just to show you that I got what I just got, is I'm going to do a common denominator and simplify. And that's what I got on the one before. Okay? So, see that? It's 3x plus 4 over 2x times x plus 1. And here I think I still have, this is not quite right. Let me back up a little bit. This should be just 3x, not 3x squared. Okay? Yes?
Can you explain the first step right there? When you got to 2 ln x minus 1/2 ln x.
Okay, so this is just rewriting this log of x squared over square root of x plus 1. Remember, everything that's in the top of the fraction we take as positive, so we take out the 2 log of x, so that's the log of x squared. And then in the denominator we have this as minus, because that's 1 over the square root of x plus 1. Square root has an exponent of 1/2, which makes a coefficient in front of the log, and then it's going to be just the log of x plus 1.
Okay.
Now these two derivatives are really easy then. Okay, so all the work was going into splitting it in two, and in fact even if I had like an x squared or something like that in here, it'd still be easy. It'd just be multiplied everything by 2x, right? So that's the way to do these. Okay, so I'd like you to try this one. Find the derivative of this. Okay, use that same technique. Don't try using the quotient rule after you've done the chain rule. Okay, so let's first rewrite it. And now we'll take the derivative. Okay, and we'll call that done.
I did x plus 2 instead of x plus 1.
Yeah.
Yes, you just take the reciprocal of like x minus 1, right?
Mm-hmm. Yeah, the log is just the reciprocal. The derivative of the log is just reciprocal. Yeah, you know, it's one of those things where once you see e to the something or the log of something and you're taking derivatives, you get used to the form of them, and then all of a sudden they become very easy because there's not a whole lot of computation. Okay, so now, logarithmic differentiation. That was pretty cool, right? I mean, we could avoid using the quotient rule completely with polynomials by having this logarithm. So there's nothing that says that we can't use this in ordinary differentiation. Okay, so let's say I have y equals x to the fourth. Now you know what the derivative of this is, right? It's 4x cubed. All right, you should know that one in your sleep. But let me just demonstrate what logarithmic differentiation is about with this one, just to show you the process. Okay, so first thing we're going to do is we take the log of both sides. And then I'm going to take out that fourth now as a coefficient in front of the log of x. And now what I'm going to do is I'm going to do implicit differentiation. Okay, so the derivative of the log of y is 1 over y times the derivative of y, right? That's by the chain rule. The derivative of 4 log of x is just 4 over x. Okay, so now, just like we do with implicit differentiation, is I'm going to solve for y prime. And so I get y prime equals y times 4 over x. Not as satisfying because I have a y in here. But I know what y equals. Y equals x to the fourth. So if I put in an x to the fourth, what I get is, when I simplify it, I get 4x cubed. Okay, that was way too much work for just taking the derivative of y equals x to the fourth. But think of all the time that you can save by doing this with ratios of polynomials. Okay, so I'll get into one that's a little bit more complicated. Okay, everybody with me here? Okay, so let's say this one. Not a very fun one to do with the quotient rule, right? Because you have, in the numerator, you're going to have a product rule and a chain rule. The bottom one, you know, that one's straightforward enough, but it's just going to be a mess. So let's first take the log of both sides. And now what I'm going to do is I'm going to simplify this thing according to my log rules to be this expression here. Okay, so the x squared turns out to be 2 log of x. The square root of x plus 1 turns out to be 1/2 log of x plus 1. And then what's in the denominator is a negative, so that's negative 1/2 log of x minus 2. So now I'm going to take the derivative of both sides. So the log of y, just like I had before, the derivative of the log of y is going to be y prime over y. Now let's take the derivative of the rest of that expression. So we have 2 over x plus 1 over 2x plus 1 minus 1 over 2x minus 2. Okay, that was straightforward enough. There's really no chain rule to worry about because those are all linear expressions in there. And we've just essentially taken the reciprocal of the argument of the logarithmic function. Okay, so now we have multiply both sides by y, and we know what y is. Y is our original expression, so I'm just going to pop that right back in there. And so I get this business here. Way easier than the quotient rule, way more reliable, right? Because there's really not that much to keep track of. We do a good job of splitting up the logarithmic expression into something that is very, very simple to take the derivative of. And then we just multiply that by our original function. Now, certainly, we can find the common denominator, multiply all this stuff out, and get a simplified version or a unified version of it. But it's probably not going to be any simpler from a calculation standpoint than if I wanted to evaluate what y is if I know that x equals 3.4. This is pretty straightforward on your calculator. Okay, so we can stop here. And if you're going to use this method, I don't expect you to simplify it beyond this. This is actually very self-descriptive. It's the original function times these three terms. Okay, so I just wrote out the procedure so you can refer to it when you're doing your homework. So the first thing you do is you take the natural log of both sides. Next thing you do is you expand that log and simplify using your log rules or your, the equivalent expression kind of thing. And then you differentiate both sides. Do it implicitly, so you end up with y prime over y equals the derivative of that other side. And then we're going to solve for y prime. So this is why it works. Okay, if we're going to take the derivative of the function, first step is take the log of both sides. Second step is implicitly differentiate both sides. So this turns out to be y prime over y. The derivative of the log of f at x is just 1 over f at x times the derivative of f at x. And then when we solve for y prime, we get y f prime at x over f at x. Notice that y and f at x are the same thing, so that cancels out. You just get the derivative equals, y prime equals the derivative of f. So this is a little bit of smoke and mirrors here, in a sense, in that we're doing a transformation, doing an operation on it, and then the transformation undoes itself when you substitute back in the original y. And so you know that this will work when, if you take the log of something, you get something that's simpler than the function itself. And remember that last one where I had that that rational expression where you had, some square roots in there, you had some exponents of polynomial expressions. If we expand that by taking the log of it, so we get all these simpler expressions, this is going to be the easier method. You don't really even have to have anything other than a rational expression to make use of this. Okay, so we have 5 minutes left. So instead of you doing this, I'm going to do it, okay? And then you can listen to it back and practice on the homework tonight. Okay, so I'm going to take the log of both sides. Going to expand that log. Now I'm going to take the derivative of it, solve for y prime, and put in my original function instead of y, and I have it. Now, there's also a case here where if we have this function, y equals x to the x. Now, if you have x to the fourth, you know how to take the derivative of that, right? Or if you have 4 to the x, you know how to take the derivative of that. We don't have any real way of doing this. But logarithmic differentiation works here as well. So if we take the log of both sides and make that x log of x, now do our differentiation and use the product rule here. We got derivative of x times the log of x, and then x times the derivative of the log of x. And so this simplifies out to be this. And so there's the derivative of one that would seem like almost an intractable problem. How would you do that? There's no rule that you have. The logarithmic differentiation works here.